Welcome back to Contemporary Math. What we'd like to do in this video is continue taking a look at apportionment methods, finishing up with our introduction. So for the last bit of our introduction, what I'd like to do is I would like to take a look at the standard divisor and the standard quota for essentially the same example that we looked at initially. But what I'd like to do is, right, we already observed, or we can observe, that the standard divisor, as we calculated it the first time, was 10, because we could find all of the numbers, how many doctors each clinic should get, by dividing by 10. And that would be the standard divisor. Divide by 10, we get how many doctors they need. So standard divisor. And then the standard quota, that is the amount that's supposed to be apportioned to each. So the standard quota for each was the number of doctors they get. So 6 doctors, 12 doctors, 18 doctors, 6 doctors, and 18 doctors. That's the standard quota. We have a quota for each of the groups, whereas the standard divisor is used, same divisor is used for all groups. So we want to repeat this, but what we want to do is we want to recognize that there will be situations where the numbers really don't work out so nicely. So let's take a look at essentially the same example, but what we want to do is determine the standard quota if there were 64 doctors instead of 60. So 64 instead of 60, like the previous problem. So the first thing we need to do, so first, find the standard divisor. Well, the standard divisor is just the population divided by the number of items to be apportioned. So in this case, 64 doctors. And if we evaluated that using a calculator, we would find that it is 9.375. So then we can find the standard quotas. So to find the standard quota, we just take the population of the individual group and we divide it by the standard divisor. So for clinic A, the standard quota is given by the 60 patients they see a week divided by 9.375, the standard divisor, and that comes out to be, okay, so we have more doctors to distribute among the clinics, so we should expect that they get more doctors since there are more doctors to distribute. But what happens is we end up with 6.4. Well, that doesn't necessarily make sense. I can't give out 4/10 of a doctor. So what does that mean for us? Well, first, let's find out what all of these standard quotas are. So the standard quota for clinic B, let's see, they see 120 patients each week divided by the standard divisor of 9.375. That gives us 12.8. which is, again, slightly larger than the quota found previously, which makes sense. There are more doctors. So clinic C, their standard quota would be the 180 patients they see each week divided by 9.375 to give us 19.2. And then clinic D, they see 60 patients each week like clinic A. So the standard quota for clinic D is also 6.4. And for clinic E, the standard quota for group E is going to be the same as, or for clinic E is going to be the same as clinic C, since they also see 180 patients each week. So this is 19.2 as well. And we can't distribute 4/10, 8/10, or 2/10 of a doctor, but we should notice that if we were to add all of these up, we do get that we have distributed the 64 doctors. So if I add up what's been distributed to all of the clinics using these decimal forms, I would find that this is in fact equal to 64. So that's perfect. But the thing is again, we cannot distribute 4/10 of a doctor. That does not make sense. So how many doctors should clinic A really get? How many doctors should clinic B really get? Well, maybe we just want to round them. Maybe it would be 6, right? Rounding to the nearest integer. So 6, 12, 19, 6, and 19. If we added those numbers up, we would have 6 plus 12 is 18, plus 19 is 37, plus 6 is 43. 43 plus 19 is going to give us 62. So 2 doctors short, so they haven't all been distributed. So how do we handle that? So that's not quite how they should be apportioned either. So this is what the investigation is. This is what the apportionment methods give to us, right? How do we handle distributing these doctors? We know, or we would expect it to be, something really close to what that standard quota is, and that's exactly correct. In fact, every apportionment, every way that you decide to distribute the doctors or whatever it is that you're distributing, every time you do that, it should be that standard quota rounded up or rounded down. When we round the standard quota down, it's called the lower quota. And when we round the standard quota up, it's called the upper quota. And the expectation is that every time you distribute the items, whatever they are, to the different groups, each group should receive either the lower quota or the upper quota. If they receive more than the upper, that would be unfair because they're getting more than they need. If they're getting less than the lower quota, that would be unfair because they're getting less than they need, right? It becomes unfair. So fair would be to receive the lower quota or the upper quota. And this idea of that it should be the quota that's received each time is given by what's called the quota rule. So that is the quota rule. All right, so this is the goal of our apportionment methods. We'll take a look at 3 of them: Hamilton's method, along with Jefferson's method, and then finally Webster's method. The 4th method, I would like you guys to take a look at yourselves because it lines up so closely with the 2 preceding methods that it becomes a little bit redundant for us to look at it together, but it becomes a great thing for you to look at on your own. And again, the directions or reading through this should make a lot of sense once we've looked at the preceding 2, and the answer that you should find is actually even given. So that should be something really easy for you to approach on your own after we've taken a look at the preceding 3 methods. So we'll go ahead and take a look at those in the following videos. I'll see you guys again shortly.